Okay, I believe I'm now live. So yeah, hello everyone and welcome back to today's live work. Where today we are gonna be talking about um diff, diff diffusion. So yeah, and yeah, basically for today I will just actually be doing a lot more streams because yeah, today is a holiday, and then after this we have the quiz, and then after that we got the final exam. So yeah, I will later just need to just to So yeah, I will just do two different streams to do both of them, and then after that it would be the final exam, and then after that I can actually do some other courses. So yeah, without further ado, let's just actually go and just get started first. But yes, I know that I have a little bit of an issue with my nose, so yeah. Let oh let me just fix this first. Okay, so yeah, let's actually just go and get started. Number one, diffusion through a membrane. A membrane is to be manufactured to the following specifications. At 700 degrees Celsius, the leak rate of hydrogen is not to exceed 10 to the power of negative 3 mole centimeter to the power of negative 2 H minus 1, while the concentration of hydrogen are maintained at 1.5 times 10 to the power of 18. Is that 18 or 19? 19. 10 to the power of 19 atoms, centimeter negative cubed, on one side of the membrane and effectively 0 on the other side. What is the minimum thickness of iron foil that will meet this requirement? The, the, the diffusion coefficient of atomic hydrogen in iron at 700 degrees Celsius is 3.091 times 10 to the power of negative 4 centimeters squared as minus 1. Okay, so let's actually first just write everything that we know. And then from this thing here, I can actually realize what this is. Oh, well, so yeah, this is basically Fick's first law, which is basically J equals to negative D. And then you take e to the power of... Wait, what? No. Wait, what was it? What was Fick's law? Wait, let me just get my book. Is it the change of concentration? Let's see. Okay, diffusion, there we go. Um, Here are the laws. So yeah. Oh yeah. It's so yeah. It is the change of C over the change of X. So yeah. C here is concentration. So yeah, we can just do that. Our thing. And so first things first that I realized is that the temperature doesn't. So yeah. That so yeah, the temperature doesn't change. Um, and then for the J. Okay, so we want the J here to be 10 to the power of negative 3. It's not to exceed. It's not to exceed. So yeah, you could just write it like that. J is less than equal to 10 to the power negative 3 mole centimeter squared hours. Yes. Oh wait, remember one thing. We need to make sure that the units will be the same. So yeah, we can just later just do that. This is mole centimeter negative 2 H negative 1. There. And then after that, we also have the d here. The d in here is 3.091 times 10 to the power of negative 4 centimeters squared with s to the power of negative 1. And so with this, okay, we can actually just start by converting this guy here. Oh wait, no. When the concentration atoms centimeter. Okay, okay. So yeah, in here, let's try to find the change of concentration, which in this case is the change of concentration in here would be 1.5. So yeah, so one side is 1.5 times 10 to the power negative 19, and then the other side is effectively 0, so we can just say that it's 1.5 times 10 to the power of 19 atoms per centimeter negative 3. There we go. So that's that. Um, and then, oh, yeah, and yeah, that's basically the change of C, because like from one side to the other, well, yeah, you can just write this guy as negative. So we can later just try to find the change of X. And so we can just plug in the entire numbers in. Oh wait, no, but before that, I need to change the units here. So yeah, in this case here is 10 to the power of negative 3 moles centimeter squared hour per centimeter squared hour. Um, we will change the hour into seconds. So yeah, um, so 1 hour is 3,600 seconds. So we just need to divide it by 3,600, which you can just plug it into your calculator. 10 to the power of 3 negative 3 divided by 3,600. Oh wait, but there's also something else, which is that we need to convert the moles into atoms or the atoms into moles. So yeah, you need to consider that as well. 2.78 times 10 to the power of negative 7. Yep. Moles centimeter negative 2 and h to the power of negative 1. There. Yep. No. Seconds. And so we have that. Oh, we just need to convert this DC here, the change in concentration. We just need to multiply that by the mole, which is just basically like, yeah, 6.02 times 10 to the power of 3. No, 10 to the power of 23 divided, it is per mole. So yeah, 1 mole is 6.02 times 10 to the power of 23. So we just need to mole. No, the atoms at the bottom. So you divide it. Yeah, 1.5 times 10 to the power of 19 there. You divide it by 6.02 times 10 to the power 23. This would give you 2.49 times 10 to the power of negative 5. Moles centimeter negative 3. So we can just plug it in, and then we can just change those stuff. So we know what change of x is negative d. Let me just change that. There we go. So it's negative d times dc divided by j. And so with this, we will just actually try to calculate this guy. Oh wait. Okay. So yeah. Let's see. Um. Oh yeah. We can actually just do this. Dx equals to those crazy stuff. you just need to plug it all into the calculator. Let's see. Um, negative D. So yeah, negative with negative, that's positive. So yeah, we don't need to care about that. The D here, the D in here is 3.091 times 10 to the power of negative 4. Yep. And then you multiply it by the DC, which is 2.49 times 10 to the power of that, negative 5. Okay, good, good. And then we divide the entire number with the J, which is 2.78 times 10 to the power of negative 7. Well, yeah, actually, like, yeah, this guy should be thousands of sevens, so yeah, we can just try to find the closest number. Oh, yeah, we could say that that's around 0.028. Yeah, pretty accurate. Centimeters. So yeah, we can just try to check on the units. That centimeter per s negative 1, and then after that, so yeah, the centimeter is at the bottom, and then we got, okay, so the moles at this point is moles centimeters second, moles per centimeter second. The second will cross out, the centimeter will go to the top, the moles cross. So yeah, it's 0.028 centimeters, which is basically around 2.8 millimeters or 3 millimeters. So that would so 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 that's what you need to have for this membrane. Is that you need to have the thickness of 0.028, just to make sure that just just to make sure that the diffusion rate would be that high. So yeah, that's that. Good job, guys. Okay. Um. So let's actually go to the next problem, and this is from the book, which I'm scared not to actually to post it because, like, yeah, it might cause some problems. So yeah, I just need to go ahead and just try to find the book first. Um. Let's see. Where is it? Where's the book? Um. General chemistry. I think it's at the top there. Multivariable calculus. Okay, it should be. Yeah, there we go. Introduction to materials science for engineers. Let's see here. Chapter 5. Diffusion. There we go. Chapter 5, problem 25. Let's see. Yeah, there we go. Steady state differential equation. Good. A differential nitrogen pressure exists across a 2 millimeter thick steel furnace wall. After some time, steady state diffusion of the nitrogen is established. Diffusion of the nitrogen is established across the wall. Given that the nitrogen concentration on the high pressure surface of the wall is 2 kilograms per meter cubed. Oh, let me just do that. 2 kilograms per meter cube. Calculate the flow of nitrogen through the wall in kilograms per meter squared hour. if the diffusion coefficient for nitrogen in the steel is 1.0. Oh, let me just go and enter that. 1.0 times 10 to the power of 10, not negative 10 meters squared per second at the furnace operating temperature. Okay, so this is problem 2. Okay. So the first thing that you do is to obviously just start by writing everything that is known, because this entire thing is basically from the formula, and yeah, the temperature doesn't change. So yeah, we don't really need to care about we don't need to care about the temperature independence or the or the time as well. So yeah, this is also fixed first law. So differential nitrogen pressure exists across a 2 millimeter. 2 millimeter, that would be the dx. 2 millimeter is equal to 2 times 10 to the power of negative 6 meters. Good, good. And then after that, we got the wait. A differential after some time studies is given that the concentration on the high pressure surface of the wall is 2 kilograms. We can just assume that the furnace doesn't have any nitrogen. So we could say that the DC here would equal to negative 2 kilograms per meter cubed. And then after that, and then we also got the D here, which is 1 time, no, let's just write 10 to the power of negative 10 meters squared per second. But yes, we want that in kilograms per meter squared hour, which means that we need to convert some stuff here. So yeah, 3,600 seconds equals to 1 hour. So we just need to multiply that by 3,600. Let's plug it into my calculator, which is obviously unnecessary. 3,600 multiplied by 10 to the power of negative 10. This would equal to 3.6 times 10 to the power of negative 7. There we go. Meters squared per hour. And so when you just check the entire thing, the unit should be correct. That's I think it might be correct. So meter squared with meter squared. That wait, what? The unit doesn't add up. wait, yeah, the unit doesn't add up. Wait, this guy with yeah. So that's meter squared 10 meter. No, what? It's this guy over this guy, right? Wait, what? Joe, I just got confused even more. So this guy, meter cubed, you divide the thing by this guy, so that's meter part. Oh yeah. That seems to be correct. So yeah, we just need to just plug it into our formula just to find what J is, which is the flux or the flow of nitrogen. The flow, that would be 3.6 times 10 to the power of negative 7 there. And then after that, you need to multiply that by 2 divided by 2 times 10 to the power of negative 6. That would get you 0.36 kilograms per meter squared hour. And that's that. It's simple. So yeah, this thing is not really that hard. So yeah, this is basically steady state diffusion. Pretty simple. Let's go and do the third problem here. The third problem, let's see. That's problem 26. Okay. For the furnace described in problem 2, design changes are made that include a thicker wall, which is 3 millimeters, and a lower operating temperature that reduces the nitrogen diffusivity to 5.0 times 10 to the power of negative 11 meters squared per second. What would be the steady state nitrogen flow across the wall in this case? Okay, let's see. Um, so there are some changes. So yeah, we just need to change a little bit. But yeah, the rest should be the same. So yeah, the first thing is that the dx actually changes to 3 millimeters, or it's 3 times 10 to the power of negative 6 meters. And then after that, the other change is that reduce the nitrogen diffusivity. That would basically be that is the D. This would equal to 5 times 10 to the power of negative 11. So this would equal to, so yeah, you just need to multiply that guy by that other guy. 5 times 10 to the power of negative 11. Multiply that by 3,600. Oh wait, I forgot units. Oh wow. Meters squared per hour. Second, hour. Yes, seconds. And so, what you'll get is actually 1.8 times 10 to the power of negative 7 per hour. And so you can just plug the entire numbers in. So yeah, the DC is still the same. Yeah. So that means that we can get the J here to be, plug them all into the calculator, 1.8 times 10 to the power of negative 7. Multiply it by the DC, which is 2. Divide the number by the 3 times 10 to the power of negative 6. And the answer is 0.12. Does this make sense? It should actually just differ like around the factor of 3 because of the changes of the factors. So yeah, 0.12 kilograms per meter squared hours. And that's J. I solved J. Yes, that's the answer. Good. So lastly, it's problem 27. Okay. Let's just write that in. For, wait, let me just check this guy here. Okay. So number 4. Many laboratory furnaces have small glass windows that provide visual access to samples. The leakage of furnace atmospheres through the windows. Oh, let's just enter that. There we go. Of the windows can be a problem. Consider a 3 millimeter window of vitreous silica in a furnace containing inert oh, inert helium atmosphere. For a window with a cross-sectional area of 600 millimeters squared, calculate the steady state flow of helium oh wait, let me just add that in just to make sure that the grammar is correct. Helium gas in atoms per second, okay, across the window if the concentration of helium on the high pressure furnace surface of the window is oh is 6.0 oh wait, did I just cancel that? Okay, let's open that back up. 6.0 times 10 to the power of 23 atoms per meter squared, no, meter cubed, and on the low pressure outside surface is essentially 0. Oh, that would make all of the calculations simple. The diffusion coefficient for helium in vitreous silica at this wall temperature is 1.0 times 10 to the power of negative 10 meters squared per second. Okay. So yeah. So this thing would literally mean that, yeah. First thing, let's just go ahead and just write everything that we know. First thing that we got the thickness of the window, which is the dx, which is 3 millimeters, or 3 times 10 to the power of negative 6 meters. And then after that, for a window with a cross-sectional area of 600 millimeters squared. So, okay, this is gonna be something else, because like, oh wait, no, actually it's possible for you to calculate it. Yeah, let's actually just try to do that first. But yeah, the DC here I know is negative of this other guy, which is 6 times 10 to the power 23 atoms per per meter cubed, because like, yeah, that's the sum of the particles per volume. That's basically concentration. And then this diffusivity is equal to 10 times 10 to the power of negative 10 meters squared per second. So actually we can actually just really plug it into the formula, because like, yeah, the bottom side will be meter to the power 4 seconds atom, and then after that you just plug in the area, and yeah, that should work, as the units would be correct. Like, yeah, every single time when you just try to solve physics or chemistry problems, just make sure that the units make sense. So yeah, let's just go ahead and just plug it in straight away. So what's the J here? The J here would, let's just plug it into our calculator. We can use the same formula. So we would get 10 to the power of negative 10. Yep. Multiply it by 6 times 10 to the power of 23. And then this guy here is divided by the change of x, which is just this 3 times 10 to the power of negative 6. We would get it to be 2 times 10 to the power of 19. So it's 2 times 10 to the power of 19 atoms per meter squared seconds. But what we have is millimeters squared, so we just need to convert them all. So yeah, basically from meter to wait. Oh no. After all this time I just convert millimeters into the wrong units. Oh my. Oh my, okay. So I just need to plug that in into negative 3, so this guy should be 360. Well, now the units work. Now. It works just now. Ah, wow. Why didn't I check it first? So yeah, you just have 10 to the power negative 10. That's negative, that's 2. Then you divide it all again. Which would get you to another number. Oh wow. Aye. It's now the unit. Wait. Does the unit now make sense? That's the problem. Oh wow. 10 to the power negative 4. Okay. Something doesn't work. Something doesn't work here. Let me just recheck this. 3.6 times 10 to the power of negative 7 here. Multiply that by the DC, which is 2. Divide it by the dx, which is 2 times 10 to the power of negative 3. It's 3.6 times. Okay. 3.6 times 10 to the power of negative 4. So yeah, it's much more smaller. Well, not this one. Copy that. Paste that there. So this guy here would be 1.8. No, 1.2. That was what I got it. Wait, did I last time got that? Yeah, I think so, yeah. So that's the real number. Good. I found it. And so with this guy here, we just need to go ahead and just convert the meters into millimeters first. So yeah, 1000 millimeters equals to 1 meter. That's 10 to the power 3. That means when you square it, it's 10 to the power 6. So 10 to the power 6 stuff. Oh wow. 10 to the power 6. 10 to the power 6. Wait. 1 meter squared is 10 to the power 6. So we just need to yeah, we can just divide it all just to get this guy here. Atoms per millimeter squared. Good. Second. And so you can just plug in the entire numbers in, which is just by multiplying it by the 600 meters squared. What you'll get is actually 12 times 10 to the power of 13. Multiply that by 900. No, 600. That would get you. Wait, what? Oh yeah. that would get you 1.2 times 10 to the power of 16 atoms per second. So yeah, we could say that it's a pretty small number compared to a mole. And that's the answer. Yes, we have finally solved this problem of diffusion, which is something that I'm pretty impressed, because like, yeah, I didn't realize how easy those problems are. So yeah. So yeah, we can just finally do some diffusions. So okay. So I think I'll also just add in um I will, yeah, I will just also add in the quiz stand, and then after that I will have like another stream on doing the final exam. So yeah. Um okay. So yeah, let's just actually go straight away. Let me just screenshot this first. That's the first thing that I need to screenshot. Oh. What just happened? Let me just see the screenshots, just in case. Is the screenshots fine? Yeah, it's fine. Well, let me just check my OBS just in case that the thing. Nope, it's fine. Good, it's fine. So let's just add in my new page here. Well, yeah, it's not really a new page. It's a new document. This is called quiz 10. Wait, quiz 10 or quiz 11? Quiz 10. Wait, so what did I just did? Quiz 9? Okay. So yeah, I will later just need to rename a little bit of my stream, so yeah. Oh, can I edit it now? Yeah, I can edit it now. And quiz 10. Wait, what? Haven't I actually done quiz? Wait, what? Chumet got more confused. Okay, so okay. That's something. And quiz 10 3.091 MITOCW. Save. There we go. So yeah, basically when you have quiz, you are not allowed to have those cheat sheets. But yeah, you know what? I'll just use it a bit. So yeah. Um let's actually just place in. Let's place the first problem here. There we go. Ooh, that is pretty big. Let's shrink that down. There we go. So here we go. Now let's actually start this. You want to know how quickly your MIT acceptance balloon will run out of helium gas inside it. Since you tie the balloon so tightly, you neglect the pinhole at the neck and model the balloon as a closed sphere of latex. Good. The balloon is 0.1 millimeters thick. Okay. When we have something with thickness, I know that this thing must be dx would equal to 0.1 millimeters. Or we can just basically state that, yeah, this guy here would be equal to a 10 to the power negative 1, so that would be 10 to the power negative 4 meters. Why not? The concentration of helium inside the balloon is 0.04462, and outside the balloon is 2.32 times 10 to the power negative 7. I would just neglect the outside volume because oh like yeah because like of the because of the very small number, I would just neglect the number. That's 0.04462 molars. Yeah, pretty accurate because like yeah, it's like it is a very small number, which shouldn't really affect a lot. If the diffusivity constant of helium through the latex is 7 times 10 to the power negative 9. Okay, so that's the D here. Oh yeah, by the way, I need to turn that to negative. Um, is 7 times 10 to the power of negative 9 meters squared per second. At room temperature, what is the flux of through the latex balloon? Wait, why do you have L? What's 1L? What? Why do you have an L? Hint, 1L is 0.001 meter cubed. But what is L? Latex. What is... What? Why? What? Why? When? Why? Who? Will? I? What? Okay. So yeah, let's just actually go ahead and just write them all in, I guess. Let's just straight away try to find the flux. So, you put J there, and then you just plug in the formula of negative D, 7 times 10 to the power of negative 19 to the power of negative 9, and then after that you multiply that by the TC, which is 0.04462, which is pretty accurate, and then you divide it by the dx, which is 10 to the power of negative 4. Okay, so what you'll get is actually 3.1234 times 10 to the power of negative 6. Wait. Wait first. Sorry about that. So yeah. So yeah, what you'll get is actually 3.1234 times 10 to the power of negative 6, which is pretty accurate because of well yeah. Oh well yeah, the error would be like a couple percent. So yeah. So yeah, you don't really need to care. Wait. I didn't consider the units, man. Okay. So what is 1 molar? Well, that's a moles per volume. Yeah. That's mole per meter cubed. So so yeah, the units would be moles per meter squared. Wait, why do you have 1 liter? Wait, do you use liters? You do use liters, yeah. So that's liters. That's moles per liter. That's true. Which would mean that, yeah, I need to convert the volume first. So yeah, that's 1 liter. Oh, L is liters. So 1 liter is 0 point that. So you just need to divide it by 0.0001. Divide by 0.001. There we go. I believe so because like that's how I do it. So when you just divide it by 0.001, that would equal to 44.62 moles per liter. Moles per meter cubed, okay. And so the entire unit should work. And so what we will get is actually 3.1234 but the power is actually 3. Good. That's a quick way, I guess. And then after that, okay. Part 2. You're shocked to discover that the helium gas is diffusing through the balloon so quickly. In order to preserve the cherished memories of your MIT undergrad, you decide to slow the diffusion of helium through the balloon. Okay. What concentration of helium gas would you have to have outside the balloon to halve the flux? Okay. Um. So yeah, this thing basically asks about how. So okay. So yes, my first intuition is to just to write j equals to negative d of dc over dx, and so we have j1 and j2. The d is a constant, the dx would be the constant, but the dc would be something that would be changing, and so we just need to use some math stuff. So yeah, j1, which is the initial, and then you want to halve the flux, so that would be 2j2. Wait, really? No, you want to halve it. So yeah. So J1 is the initial condition, and now J2 is the thing that we want. So yeah, we want J1 to equal to half of J. No, 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 no. J1 must equal to 2J2 because we want to halve the flux. Yes, that's true. So we can just plug it in. So what you'll get is negative d of dc1 over dx would equal to negative 2d of dc2 over dx. We can cross out the dx. That's the first thing that we can do. The second thing is we can cross out the negative and the d, just to get that you need twice the concentration to halve the flux. What? With what? With what peanut butter in the toast? What? If you want to put... No, 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 wait. You want to halve the flux, right? So that means that it must be... So J1 must equal to 2J2 because of the stuff. D would cross out, dx would cross out, so yeah, it's just a simple stuff. Oh, so yeah, dc2 would equal to... oh my, oh wow. So yeah, dc2 would equal to that. And yeah, by the way, I don't... Like, yeah, initially that we have the DC of 44.62 plus or less. So now we will have it to be... So the DC in here would be 0.02231. There we go. Some quick maths inside my head. Moles per liter. And so we know that the concentration required would be the initial concentration minus the final concentration. Oh yeah, don't forget that this guy is a negative number. Yeah, it should be a negative number. So yeah, C2, the one outside, minus C1, the one on the inside, must equal to DC2. That means C2 must equal to that guy plus that other guy, which would equal to 0.2231. 0.2231 molars. There we go. And that's the answer. So you just basically halve the thing. And so yeah, that's basically a little bit of some math manipulation, because obviously science uses lots of math manipulation just to halve it or to double it or both. So let's actually take out our next artboard. Let's put in our the questions. Ha, there we go. Ah, perfectly lined. That's perfect. Okay. At what temperature would you have to store the balloon to halve the flux? Compared to question 1. EA equals to 0.09 electron volts, which would equal to 1.44 times 10 to the power negative 20 joules. Okay, so this one basically uses your D. So when you just actually just assume DC over DX is the same, you can just ignore that. But we still want to halve the flux, which means that J1 would equal to 2J2. This is still the same fact, and so we know that D1 must equal to 2D2. But we know some fact is that for D it would equal to Svante, which would equal to the A would, so yeah, basically the constant, the D naught would cancel each other out. And so what you'll have is actually something with something else. Yeah. So D naught and the other guy would actually just cancel each other out. So you'll get some maths. The D naughts. Let's see. Wait, what? What? Joman's brain just got crazy. Uh, oh, it's e to the power of negative EA over KBT. Yeah, that's that. Equals to 2e to the power of negative EA over KBT. KBT. There we go. So now we need to take the natural log of both sides. Why? Just to make sure that we can calculate things easier. Obviously. Obviously. Oh wait, no, sorry. This comes to be T1 and T2. There we go. So according to maths, things should work. Well, yeah, at this point I'm just trying to find what T2 is. So my first intuition is to just basically take the natural log of both sides. Must equal to natural log of 2 plus that other number, just negative EA over KB T2. Which is something that I need to calculate now. Unless I don't want to. Which could be the answer. So yeah, you can just take it EA over KB of T2 minus T1 there. Sure, why not? That's equal to natural log of 2. Okay. And then after that, no, no, that doesn't work. It should be something like that. Yes. So what you'll get is actually that, yeah, this guy must equal to something else. So 1 over T2 minus 1 over T1 would equal to KB of natural log of 2 divide the thing by the EA. And so you can get 1 over T2 would equal to KB of natural log 2 over EA plus the 1 over T1. Which is something that I don't know. Good. Very good. So we can just plug the entire thing into our calculator. So KB is the Boltzmann constant. And to find the Boltzmann constant, you can just actually use some other stuff. But yeah, I'm gonna use 8.314 first. That's basically the ideal gas constant. And then you just need to divide it by the Na, which is the Avogadro's number, just to get your Boltzmann constant. And then after that, you multiply that by the natural log of 2. There we go. There we go. The natural log of 2, there we go. And then after that, you divide the entire thing by the EA, which is, in this case, one of them is joules, not electron volts, so yeah, that's why I just use the joules instead. And then you add it up by 1 over the temperature. Uh, which is how many? Uh, let me just consider this. What is room temperature? 20 degrees, 24 degrees, 22.5 degrees? What is room temperature? Uh, what is room temperature? I believe it's 20, is it? No, 25? Let me just search that up because like my brain doesn't work. Room temperature. I believe it's like around 20 to 25 degrees Celsius. Like yeah, we use Celsius. Yeah, 20 degrees Celsius. Wait, what? Room temperature for IPAC is 25 degrees Celsius. 25, okay. I'll just use 25 degrees Celsius. So yeah, 1 over 273.15 added by 25 degrees Celsius, that would be 290, 25, 298.15. So you'll get that T2 would equal to, okay, so you want to take 1 over the answer, 248.83 kelvins, which would equal to around, so you subtract them by 273.15 to get yourself negative 24.31 to 32 degrees Celsius. Okay, so that's that. Good. We found the temperature. Okay, part C. Your beloved balloon. What? Your beloved balloon is exposed to the Boston winter. It lowers the temperature of your balloon below the glass transition temperature of the latex. How does this affect the diffusion of helium through the balloon? What? Okay. How does this affect the diffusion of helium through the balloon? Does it go faster or slower? Uh, it lowers the temperature below the. So it's now at the glass state? No, it is a super cooled one. It like it doesn't pop though. According to my logic, okay, because like yeah, because of its lower temperature, it would be slower. Diffusion goes slower. That's basically something that you actually consider. Okay, fine. I guess. Fine, I guess. because like yeah, because like my brain doesn't actually work that well. Oh, wait. Uh, actually, I don't really know. When it just goes into this crystallized form, it would it would diffuse much more harder because like most of them are actually crystallized now, instead of this one is instead of this one string which has thousands of holes that you can actually just pop into it. So yeah, I would say it would go slower. D. Your friend cross-linked the latex in her balloon before filling it with helium. How would this impact the diffusion of helium through the balloon? When you just cross-link something, it it becomes much more stronger And so with that cross-linking, so when you just cross-link a bit more, it would be slower as well because of the sites, because of the because of the uh because of the like yeah, for diffusion it's like it, it is like the interstitial or interstitial interstitial sites become smaller. Okay. And then lastly, name another way that you could decrease the flux of helium through the balloon. Well, you can actually just affect the temperature. That's one thing. Or maybe like this. Thickness of thickness of thickness of the balloon. Thickness of the balloon. Or density. That could also work. Or uh you could change the crystal structure of the latex. Might not work anyways. But yeah, there's like a couple ways for you to actually to engineer the latex so so the helium wouldn't actually escape out. And that's all my thinking. So yeah, that's basically the fusion for today. Okay. So yeah, I just want to say thank you very much for all of you who have actually watched the stream, even though that none of you actually are on the stream, but that's fine. So yeah, I just want to say thank you very much for all of you, and then yeah, later on I will be actually doing the final exam. So yeah, stay tuned for that. Thank you, and see you guys later. Good.